now some intuitions to this definition. So remark. So intuition is like that quantifier-free formula is like system of equations and inequalities. It's a good intuition. So. Yes, so some conjunction of statements like something is equal to something or something is not equal to something. And then maybe disjunction, but in this case disjunction is not so important. So such a, okay, so this condition, so if we take quantifier-free formula Vx. So saying that there is extension such that okay, so this says that this system has a solution in N. Yes, exactly exists X such that phi of X. So the whole thing, so saying that there is an extension of the structure M to N such that there is solution in N, all of this means that Vx is solvable in some extension of M. L extension. In this N. So now being existentially closed means that all solvable systems of equations inequalities already have solution in M. Anything which can be solved somewhere up can already be solved in N. So M is EC if all solvable systems as above can be already solved in N, M. Yes, so this condition is an abstract saying that this system of equation makes sense. It has solution somewhere. Okay? So it's the one which we can consider whether it's already solvable in M or not. And M is existentially closed if everything which is potentially solvable can be already solved in M. So it's like very strong notion of algebraically closed actually. Okay, so and now so some terminology. Example, existentially closed group, of course, means existentially closed model of theory of groups. Similarly, is C field, is C ring. Okay? So now, as Baran said, the theorem, what are the existentially closed fields? So a field F is existentially closed if and only if F is algebraically closed. Okay, but algebraically closed looked first as much weaker, since there are very specific equations only in one variable and just equations, no without any negations, okay? And being existentially closed looks much stronger because there is many more possible systems of equations, inequations in many variables. So this at first looks as much stronger condition. So let's see. Okay, one implication is basically what I said. So assume F is existentially closed. We want to show it is algebraically closed. So take polynomial okay, now it is one variable which is not constant, and we want to find a root of this polynomial in F, but of course we have field extension this is algebraic closure of F, which is algebraically closed. So in F-alg, this F has a root. So it is true that exists X. And this is quantifier-free formula over F. So since F is EC, we also have that this is true in F. So F has a 0. Okay, so every polynomial has a 0 in capital F, because those are just very particular quantifier-free formulas. The other way, okay. The other way, first I will cheat a little using the previous lecture, what we know from previous lecture, and then I will give another proof without cheating. Okay, so we assume F is algebraically closed. We want to show if it's existentially closed. So we take such an extension and we take some quantifier-free formula. So assume F is algebraically closed. And as in definition of existentially closed, take field extension and quantifier-free with parameters from F such that it has some solution, this quantifier-free formula, over this bigger one. Yes, and we want to get this. So aim is But now we will use that all extensions of algebraically closed fields are elementary, which we showed last time, and then it will be automatic. So first we extend this K to algebraic closure. And now we have this corollary. So since this is true in K, then by corollary above, the same is true in K-alg. So we have such a situation F, which is algebraically closed field, is a subfield of K, which is algebraically closed field, K-alg. And here, this sentence holds, but we remember that yes, I hope we still remember, we showed that any extension of algebraically closed field is elementary. So it preserves the truth of any sentence, not even like this. Completely any sentence. So this means exactly that it is also true in F. And this is what we wanted. So this is cheating in the sense that we use this, what we proved about ACF, that any extension of algebraically closed field is elementary. But now I want to give also argument, a direct argument, which will directly use Hilbert-Nullstellensatz. Okay, and it will be more using similar arguments, you will be asked to show that some other structures are existentially closed. So another argument for this implication. Yes, so now let's look how this phi can look like. Yes, we are in the language of rings, so everything which we can construct quantifier phi way is like a polynomial, and then we can say it's equal something, not equal something, conjugate, and take this junction. So it looks something like this. Okay, now it has several variables. And here we can have equality or non-equality. So I'm saying in a strange way where I don't know how to say it in a better way. Just here we can say equals, or we can say not equal. Okay, two options. Okay, so far it's more complicated, but I would like to reduce it. Okay, first I want to get rid of this, and then I want to get rid of this. We say I will get kind of equivalent statement. So the first one is easy. Okay, because if it's somewhere in some k, this is true, it means that for some I, this is true. And we can just focus on this part for this I. For this I. So we can now work only with this formula. Okay, and then there is more interesting trick how to get rid of this. Okay. So
in the beginning, we suppose that any quantified free formula in such f should be like that.
Yes, that I assume we somehow know.
Okay.
In fact, modulo, yes, if you see what can happen, how you construct using parameters from f plus times, yes, then you really get polynomials. Well, you could have polynomial equals polynomial, but then you can move on one side, it just equals 0. So it's this. So formally it's not exactly this, but modulo theory of fields, it is this. Yes, because of course formula f of x equals g of x, it's not of this form, but it's logically equivalent to formula f of x minus g of x equals 0. It's okay, it's a bit of, yes, so it's logically equivalent modulo theory of fields to such one, formally. Okay? So I'm saying that, okay, for our purposes, that if you want to just check solvability of such a thing, first we can get rid of this junction, and then we can get rid of this negation of equality. Why? Because so always if we have some Fij, so if we have exist x is not 0, then this is true if and only if exist x exist t such that fjx times t is 1. Okay. Something is non-zero if and only if we can multiply by something and get 1. But this is equality at the cost of adding one more variable. So fix not equals 0 can be replaced with equals. If we are talking about existence of solutions, then it's the same.
It's like showing that general linear group is a...
Yes. Okay, so I had even less sophisticated example about hyperbola and projection of hyperbola. Okay, but let me finish. So we can assume, so this has some geometric meaning, yes? We can assume that phi of x, now there are real equalities. Let's say now I'm interested how many. Okay, and we know that this is true. They are true in K. So since something like this is true in K, there is some x then these polynomials cannot generate entire ring of polynomials over F. Since otherwise we would obtain 1 as a combination, and in K we would get that exists x such that 1 equals 0. Okay, so maybe right. Since otherwise there are G1, Gk in Fx such that okay, but then there is this x, there is some a in K such that so then in K we would have 0 equal 1, but we cannot. So this is true. And then by Hilbert-Nurstellen-Satz, there is a solution in F. So this is proof with a bit less of cheating, still using Hilbert-Nurstellen-Satz. Then, huh?
What's the meaning of that?
This, that ideal generated in this ring. Because now I have 2 rings, so I made sure that in this ring. In the other as well, but to use Hilbert-Nurstellen-Satz for F, I have to generate in this ring. Okay, so usually you don't write it, but to make sure. So by Hilbert-Nurstellen-Satz, well, F1 Fk has a 0 in F, so indeed. And this is our, phi of x. So this is like more real work to show it, but all is based on the same things. I mean, using Hilbert-Nurstellen-Satz, we also prove this in another way, so it's all one circle. But I wanted to show it, so if you want sometimes, if you have relatively easy theory, there will be such problems for you, then by understanding how quantifier free formulas look like, you may try to show that your model is existentially closed. Okay? Here there were some tricks necessary. Sometimes you may see it directly. Okay, so remark exactly what you said. So removing has geometric meaning. So it basically says, if you know a bit of algebraic geometry, that Zariski open set, which is complement of surface of solution of one equation, is isomorphic to Zariski closed set. So in simple terms, there is such a bijection, for example. So this hyperbola, so given by xt equals 1, is in bijection with x is not 0. This was exactly what was happening. So we kind of started from x not equal 0, like open set, and it was in natural correspondence with this closed set with one dimension up. This was this. Okay, but still, so I think today we will not see these other examples. I will have later 8 examples of theories and then discussing what are the existentially closed structures. But so far, we don't know whether in general existentially closed structures exist at all. We saw examples in fields, but in general we don't know. Okay, so basically we want to say that yes, they exist if we assume that the theory is inductive. So that's the connection. So far there was no connection between this existentially closed and being inductive. Now the connection comes. So lemma. So assume is inductive, like groups, rings, fields, etc., natural assumption, and we have a model. Then it has an extension, which is existentially closed model. L extensions means that M is an L substructure of another L structure, but not only this, such that N is an existentially closed model of T. Okay, so there are plenty of existentially closed models if we assume theory is inductive. And again, you should think about algebraic closure. So I will not give exact proof, but proof is kind of easy and really the same as existence of algebraic closure. Even easier in a way.
I want to ask something. In the theory of groups, so as let us take a closure of a group. Okay?
In this sense? Okay.
So it must be there exists an x such that x squared is equal to 1. This must be true in this closure, right?
Yes, there must be elements of order 2. Well, neutral element is like this. You mean not neutral, perhaps? Yes.
But I mean not a neutral element.
Yes, yes. So element of order 2.
Must be.
Yes, all orders must be there. Yes, such examples I think next time we'll discuss. Yes, everything which can be, so you can think, what can you say? So for example, you can say order. So you should have elements of all possible orders. And actually infinitely many elements of all possible orders. It's one of the conditions. And there are, because you can say there are 2 elements of order 2, 3 elements, 4. It's again like, okay. So it's one of such things. But we will see that actually groups are bad in this sense for a reason I will describe next time, that it's hard and in a sense impossible to correctly understand existentially closed groups. You will see next. Yes, maybe that's the reason. Because, okay, now I'm jumping ahead, because actually they are not axiomatizable. Existentially closed groups cannot be axiomatized. And that's the model companion thing. Okay, but that will be next time. So exactly, you cannot think because the examples, they exist, they must exist. Okay, proof is again non-constructive. They must exist, but actually they are bad because they cannot be described. Okay, but this is in 2 weeks. So now we are fighting with Shaw to prove the existence. So it's, I'm saying, like for fields, algebraic closure of field. Okay, and also algebraic closure is kind of unique. In general, there is not much of uniqueness. This is existence, but there is no uniqueness in this statement. So it's not, sometimes it is a bit unique, sometimes not at all. Fields are very nice. In fields, everything is unique, up to isomorphism exists, can be axiomatized, everything. But everything may collapse from these nice things in general. Okay, so how you were proving it for fields? You were enumerating all the polynomials and adding solutions one by one. So the same here. So enumerate quantifier-free formulas over M. Okay, and we know that for each formula, if it's solvable, okay, that it has solution somewhere, so extend M to this solution. Then take another one, extend again, and continue like this. And then N add okay, but one point, so this is kind of, okay, you do it, but then you have some limit step, you have to go to the union, and this is where inductive helps. Okay, so formally this is transfinite induction, the same as for fields. So crucial moment is limit step. So here you have to take increasing union of this structures with solutions, and it's okay. This is the only moment we use that T is inductive, that it's allowed to take a union of models, and it's again a model. So after you do all of this, we are still not done. Okay, so then after this, we have extension, but here all like systems of equations with parameters from M have solutions in M1. So then we have to continue again. It is exactly what happened in the case of fields. So then we have M1. Yes, then all systems with parameters from M1 have solution in M2, etc., etc. And this N. So now it's okay, model of T, because again it is inductive. And that's it. So the same as for fields, it's even easier, because for fields you really had to construct this solution somewhere, take quotient by polynomial, and here by definition, formula is solvable if solutions exist somewhere. So you just take these extensions when solution exists. So in a way it's even easier than showing that algebraic closure exists. But we have to be able to take these unions. That's the only point here. So in particular we have existentially closed groups, existentially closed rings, all of these things we have. Okay. So I can say it. So now the main definition which all the time I was aiming for. So let T be inductive L theory, then we call an L theory T star a model companion of T. If this T star axiomatizes existentially closed models of T. So formally, I will write everything. For each L structure, we have that M is a model of T star if and only if M is an existentially closed model of T. And this is something non-trivial finally. Okay, so it was easy to see these existentially closed structures always exist under natural assumption, but model companion doesn't have to exist at all. It's usually a subtle question whether they exist. Okay, so that's in the remark. So remark a model companion of T exists if and only if, that's just another name, the class of existentially closed models is elementary. So really I'm introducing this name here. That is, it can be axiomatized. So of course if it can, then it's axiomatized by this model companion. And it's not so, okay, both, okay, actually with Özlem we are working on such things for several years. It's often very difficult to show it can be, and it's also difficult to show it cannot be And sometimes you look and you don't know what is the answer for given cases. So there are different methods for showing it's axiomatizable and not axiomatizable. And we will see some of these methods.
Actually, ask the same question for, let us first look at the class of models of T. And let us take a subclass, a special type of models of T.
Like this.
Always ask that whether there is a T star such that T star axiomatic.
Yes. There will be.
Why this is so important?
This is important. Because why algebraically closed fields are important? You can do all the Galois theory in one algebraically closed fields when you can solve everything. Okay, here as well. So you always have these existentially closed models, but if they are not axiomatizable, there is a reason, but maybe you don't know these notions. So you can always find existentially closed model, but if this is axiomatizable class, you can also find something which is called saturated. I think I didn't introduce that. So you are not only solving equations, but also infinite systems of them. So if model companion exists, you can find a really nice big structures where you can not only solve all the systems, but also infinite systems, which is sometimes important. So really proper, very big structures. Another practical reason is that, for example, model theoretically, theory of fields doesn't have any nice properties of all fields. There is no structural theory. But the model companion, algebraic closed fields, we saw. It has quantifier elimination. It has all these good properties. And it's very often like this. You start from some natural class from some natural theory in algebra, but model theoretically there is no hope it would have good properties. But theory of these big structures, if it exists, often it has good properties. And using these good properties of this theory, you can say something about original structures. Actually, many. In the examples I will have probably, let me see. So I'm starting examples. There will be 8 examples. Starting from trivial ones. So one, which is problem 2 for us. So language is empty. Theory is empty. No structure at all. So models are sets. So the theory of sets, but not ZFC, just trivial theory saying structure has no structure. It's just universe without anything. It's also a theory. Has model companion. So what can you say? Yes, when set. So what are your equations, inequalities? Just saying like x equals a or x not equals a. So to say this, to solve such things, your set has to be infinite. So which is the theory of infinite sets. Not very deep, but that's also, I guess, a good intuition. Big set is infinite set. And of course it is axiomatizable to be infinite. A bit more complicated. the theory of linear orders has model companion. Okay, so what can you say about linear order? What kind of things? Yes, you can see there are some things between 2 points, there is something inside, there is something bigger, or there is something smaller. And that's basically it. So if everything should have solution, so it should be the theory of dense orders. So between any two things, you already can find something in original structure. But also, which I actually forgot the notes, so you can always get something bigger, so there shouldn't be a maximal element, as in the original example, or a minimal one. So in short, it says without endpoints. It's without largest or without smallest element. Okay, so we showed the theory of fields have model companion. The theory of algebraically closed fields. Okay, so next lecture I will start from more examples, and then we also will get to groups which don't have model companion and rings which also don't have model companion. So for rings I will have argument. For groups it was a bit more complicated. So maybe I will say something. So okay, thanks for today.
We don't have a model companion.
Theory of groups, yes.
But the theory of groups is inductive.
Yes, so again, there are existentially closed groups, but they are not elementary class. Yes, always we have this, always. In all these cases we have existentially closed models, but maybe they are not axiomatizable. Okay.